All right, so we're going to go over some of the questions on the review. We can't go over the whole review, but everything that we're going to hit is going to be the important stuff for your test. So we're going to just start with number one. Remember, with number one, piecewise functions, we're going to make two tables because I have two pieces. And remember, there's kind of this dividing line where a comma appears or the word if. And so this is our starting point. This is my boundary. We're saying, hey, I'm going to start when x is 1. So in my table of x, f of x, I'm going to start with my first number 1. Now because of that equal to symbol here, I'm going to just make a note to myself that, hey, I'm going to use a closed circle. Now I need two numbers at least that are less than 1. So I'm just going to pick 0 and -1, but we need to understand that that goes down forever. So when I plug in 1, 3 times 1 is 3. 3 minus 2 is 1. So when x is 1, y is 1. When I plug in 0, I will get -2. And when I plug in -1, I will get -5. So you can just use your calculator if I'm going too fast for that. So we have a point at 1, 1. Now that is our endpoint. That's our boundary. So I'm going to make this larger closed circle. The rest are just points on the line, so we know which direction that we're going to connect those points. So 0, -2. I have a point down here. And then -1, -5. So I'm going to do the best I can to connect those with a line. Now that, again, goes on forever. So all x values going to -infinity. Our second piece, we're going to use orange here. And again, we're starting at 1. Now sometimes that confuses people. Hold on, I just used 1. But yeah, notice how this has a closed circle where this is going to have an open circle. So in this table, we have x, f of x. And my starting point, according to my piecewise function, is to start at 1. But because it does not have an equal to symbol, I'm going to just have a reminder that when I go and plot this point, I'm going to use an open circle. Two numbers greater than 1 are going to be 2 and 3. And again, that goes on forever. When I replace x with 1, 1 plus 2 is 3. 2 plus 2 is 4. And 3 plus 2 is 5. So, plotting these, 1, 3, open circle, 2, 4, and 3, 5. Again, giving me my direction that that's going to go. Now, you may be asked about domain and range. So our domain is all real numbers. So we can write all real numbers like that. You can say it's from -infinity to +infinity. You could say interval notation. We use parentheses, -infinity, +infinity, however you want to write it. Now our range is a little different. Notice how our range, our y value, is going up and down. We're going down forever, but all the way up to this point where our y value is equal to 1, and it's a closed circle. So our range in this case, remember with domain and range, it's always lowest, comma, highest in interval notation. So we're going to go all the way down to -infinity, all the way to when y equals 1. So because it equals 1, we're going to use a bracket. And then we have this other piece. So, or we're going to be from, what is this? So 1, 2, 3. We're going to be when y is 3, but not equal to 3, all the way to +infinity. So we're going to say 3, comma, +infinity. And because it's not equal to, we have to use parentheses. So remember, we use the parentheses with infinity because those are a concept that goes on forever. That's not a point that we can actually plot. But because we can equal 1, in this case, y can equal 1, we have to use a bracket. Now, we're going to move on to number 4. So let's take a look at number 4. Now, graph each function and describe the transformation. Talks about domain and range. So with number 4, remember this -2, remember how this is up and down, it's on the outside, inside of our graph. Remember it's horizontal, so it's on the inside, so it makes the word high. So this is talking left and right. This is kind of our slope, but it also talks about the vertical shrinking and stretching and things like that. So what we're going to say is we're going to go down 2. This is opposite of what you'd think, so this is left 4. And if you forget, you can plug that into your calculator, and it would show you on the picture that we go down to left 4. And then this, it's positive, so we're going to open up, but this technically is a vertical shrink, and then we say by a factor of whatever this number is on the outside. So in this case, 1/3. So when we plot that, we always start at 0, 0. That's where the parent function starts. And we're going to go down to left 4. And here's our new vertex. And then from there, this kind of acts as our slope, at least for absolute value functions. So we're going to go up 1, right 3, and up 1, left 3. I know it's a little bit off the graph. And you should have this vertical shrink, or this V shape that's getting wider, like that. So remember, a vertical shrink, it's like taking a big lump of Play-Doh and pressing down from top and bottom and shrinking it. Well, what's going to happen to that Play-Doh? It's going to come out and become wider. So this is correct. So vertical shrink by a factor of 1/3. Now domain and range. Domain, this is all real numbers. There's no x value that I cannot have. In terms of range, it's lowest comma highest, right? So the lowest y value I have here is -2. So we'll just talk about the range. It can equal -2. So we're going to use a bracket because it can equal -2. And then those arrows mean they go on forever, so all the way up to positive infinity. We use a parentheses for infinity. Now, you're not here in class. I'm just going over this quickly. If I'm going too fast, you can pause, you can rewind. You can subscribe to my YouTube channel because most of you haven't, so please do that. Go Tigers. Let's take a look at number 9. So here, we're going to do a lot of these. We're going to do 9, 10, 11, and 12, and then we're also going to do numbers 18 here. Now, we need to get as much space as possible, but I want you to be able to see what our original functions are. Some of these are easier. Some of them take a little bit longer. But these are going to be just one of each type that I want you to focus on. So, here's what we're going to do. 9, 10, 11, 12, and 18. All right, number 9, we're just adding. So we're going to take g of x and add that to h of x. So g of x is x squared minus 1. On my key, I didn't put in parentheses. If you want to put them in parentheses, you can. Remember, my key is posted in Google Classroom if you'd like to see that. Plus h of x. So h of x is 5x minus 3. So plus this 5x minus 3. Truly, all we're doing is combining like terms. X squared does not have a like term, so I'm going to bring that down. 5x does not have a like term. It's a positive 5x, so I'm going to bring that down. Here, I have a -1 and a -3, so that's going to be a -4. So here's what you get when you add those functions together. Now, for number 10, we're subtracting, so we have to be careful with our minus sign. So h of x comes first, so we're going to say 5x minus 3. And this whole function is being subtracted by f of x, which is -3x plus 2. Some of you can just look at this and subtract in your head. 5x minus a negative, oh yeah, that's positive, so it's really saying 5x plus 3x. And you can just do that, skip a step, that's fine. But others prefer to just go ahead and distribute that negative right away, get rid of it, and then now it's just an addition problem where you're combining like terms. So when we do that, we get 5x minus 3, nothing changed here. A negative times a negative is a positive, so positive 3x. And a negative times a positive is a negative, so minus 2. From here, we combine like terms. I have a 5x and a 3x. That gives me 8x. I have this -3 and this -2. That gives me a -5. And then that would be our final answer. So with subtraction, just be careful with this minus sign here. Now I want you to remember the difference between the dot representing multiplication and the open circle representing composition of functions. That's the substitution method. So just be careful. That is not saying multiply. Number 11, f times h of x. So we're multiplying, so we have two sets of parentheses. F of x. So this is -3x plus 2 times h of x, which is 5x minus 3. So from here, we're going to distribute. So distributive property, negative 3x times 5x is a negative 15x. Negative 3x times negative 3 is a positive 9x. 2 times 5x is a positive 10x. And then 2 times negative 3 is a negative 6. So from here, we want to combine any like terms that we have. Oh, I made a mistake. Do you see it? Negative 3x times 5x is negative 15x squared. Sorry about that. So the x times x is x squared. Combining like terms, we have these two like terms in the middle. So as I copy these down, I have this negative 15x squared plus 19x minus 6. Number 12, division. So with number 12, we have f divided by h of x. And again, order matters. So f of x is negative 3x plus 2. So that's going to go in my numerator. So negative 3x plus 2 are in the top part of my fraction. Divided by h of x, which is 5x minus 3. So 5x minus 3. All right, good news, bad news. Good news, you're done with that part. Bad news is there's that one step farther. You have to find the domain restrictions. So remember, we talked about in class how you cannot divide by a 0. So I have to figure out what number can I replace x with that would give me a 0 in the denominator, because that is a number that I am not allowed to have in my x values or my domain. Okay, so how do we figure that out? We're going to take whatever our denominator is. So in this case, that is 5x minus 3. And we're saying this cannot be equal to 0. So from here, we're going to solve for x, so we're going to add 3 to both sides. And we get 5x equals positive 3. Then we're going to divide both sides by 5. And so we get that x cannot be equal to this fraction, 3 over 5. So what we're saying is the only x value from negative infinity to positive infinity that I cannot have is when x is a positive 3 over 5, because if I were to plug that in for x, that would give me a 0 in the denominator, and I cannot divide by 0. So if you put that in your calculator, you would get an error message, because that is a domain restriction. So finally, number 18, we have g of h of x. So notice the difference between the open circle and kind of the dot. This is not a multiplication problem. This is a substitution problem. So from here, we look at our innermost function. So whatever's closest to our variable is going to be our input. So we're going to take h of x and we're going to substitute that in to g of x. So everywhere I have an x in g of x, I'm going to take that x out and replace it with my entire h of x function. So instead of x squared minus 1, x is being represented by h of x, which is 5x minus 3. So it's this that is being squared and minus 1. So I took x out and I replaced x with the entire function 5x minus 3. So it's this that is being squared and then minus 1. Now be careful when we square something in the parentheses. A lot of people want to just square the first term, square the last term, and you're 2/3 of the way right. But you miss that middle term. So what I think is easiest to do is just set up our two sets of parentheses. So we get 5x minus 3 times 5x minus 3. And then we have that minus 1 on the outside we haven't done anything with yet. From here, you would distribute. So go through that process. So 5x times 5x is 25x squared. And you're like, yeah, I would have gotten that if I did it my way. And you're right. But here's where it is different. 5x times the negative 3 is negative 15x, and then this negative 3 times 5x is another negative 15x, which are going to be like terms that we're going to combine, and that is not 0. And then finally, negative 3 times negative 3 is a positive 9. So this is where I said you're 2/3 of the way right. You would have gotten the first term right and this last term right, but you would have missed out on this middle term. So when I combine like terms, I get 25x squared minus 30x, and then a positive 9 minus 1 is a positive 8. Again, if we're going too fast, you can always pause, rewind, review it, get those view counts up, you know what I'm saying? Subscribe, whatever you want. we're going to take a look at 21, and then we're going to come down here to 23. So we're going to look at 21 and then 23. All right. 21, let's take a look. So, what are we doing here? We are trying to see, hey, are these inverse functions or not? So it says verify that they are, so we're assuming they are. But let's see if we can figure it out. The way we solve to see if something's an inverse function, I'm going to just replace this f of x with y. So y equals negative 5x minus 11. Remember how when we graphed, we took the x and y coordinates and then we flipped them? In the same way, I'm going to take x and y and I'm going to flip them. So instead of y equals, I get x equals. Instead of a negative 5x, I get a negative 5y. And then I write everything else the same. So all I did was take my x and y and flip them. Don't make that harder than it is. That's all you do. There's really two steps. Flip x and y, and then solve for y. So from here, we're going to add 11 to both sides. When I do that, I get x plus 11 equals negative 5y. From here, I need to get y by itself, so I'm going to divide by negative 5. And what's interesting is I get this x plus 11 all over negative 5, and this gets my y by itself, but this is my inverse, so f inverse of x. Now, is that what I see here? It is. So those are inverses of each other. Finally, number 23. Let's take a look at this. So how do I graph a function and its inverse? So I can't slide that up anymore, so sorry about that. So graphing a function and its inverse, one thing that we want to do is we want to graph y equals x as a dotted line. That way we show that line of symmetry. So here is our y equals x. So this is y equals x. That is our line of symmetry. Then I'm going to use blue to represent our original function f of x. Remember, our y-intercept positive 6, we're going to go up here, place our point. That's our starting point. Our slope here, those are our directions to go from one point to the next. So I'm going to go down 1 and always to the right. So down 1, right 2. Down 1, right 2. Down 1, right 2. I get enough points to connect these with a line, and that goes on forever in both directions. And this was my original. This was my f of x. Now, you really only need 2 points for a line, but let's do 3. You don't have to write the coordinates for all 4. But let's pick 3 points. So this point right here is 1, 2, 3, 4, 5, 6, comma, 1, 2, 3. So this is 6, comma, 3. So we're going to put 6, comma, 3. This point right here is 1, 2, 3, 4, 1, 2, 3, 4. So this is 4, comma, 4. So this one right here is 4, comma, 4, right there. And then finally, let's do this one. So this is 0, comma, 6. That was our y-intercept. So 0, comma, 6. You could have picked this one. I just didn't. Now, that is our original function. Let's see what the inverse is going to be. Our inverse, remember, we're going to flip x and y. So instead of 6, 3, I'm going to graph 3, 6. Instead of 4, 4, I'm going to graph 4, 4. So those are the same. It makes purple for tigers. Instead of 0, 6, I'm going to make 6, 0. And then I'm going to connect these the best I can. And if I would have done this perfectly, then what we see is, from this dotted line, if I could fold this over that dotted line, then we see that everything on this side would match up with everything on this side.